L'Hopital's rule is kind of fun when you see it at the end of an AP class. This used to not be on the calculus AB test, but it is now, so let's make sure you understand what L'Hopital's rule is. Let's make sure you know where L'Hopital's rule comes from, or show that it works. And L'Hopital's rule can only be used to evaluate some limits, not all of them, so you have to understand when L'Hopital's rule applies. So something else, we're getting you ready for the calculus AP test, which means not only do you have to be able to use L'Hopital's rule, but you need to understand and be able to write down certain things that you might not if you were just solving a problem. Like when you're using the mean value theorem, you have to make a couple of statements first before you actually use the mean value theorem. Same idea applies here with L'Hopital's rule. Whenever you're given a limit to evaluate, like this one, the first thing you should do is try substitution. Okay, so if we're going to substitute 3 into x squared minus 9, we get 3 squared minus 9, which is 0. And then 3 into 3 minus 3 gives us 0 over 0, and that's indeterminate form. Meaning, oh, we can't do it that way. So maybe we rearrange. Let's rewrite the limit as x approaches 3. Let's factor x squared minus 9. And what does it mean to say x approaches 3? It means we're going to use numbers like 3.1, 3.01, 3.001, 2.9, 2.99, 2.999, and so on, and look for a pattern in the outputs. Well, let's think about this. What's 3.1 minus 3 over 3.1 minus 3? 1. 3.01 minus 3 over 3.01 minus 3? Also 1. When's the only time x minus 3 divided by x minus 3 isn't 1? Well, when we're using 3. But we're doing the limit as x approaches 3, so we're not really substituting anyway. And so now you're substituting 3 into x plus 3, which happens to be continuous everywhere. And so we just get 6. We're going to come back and redo this limit using L'Hopital's rule in a few minutes. Let's show you what that is. So when can you use L'Hopital's rule? Well, you can use L'Hopital's rule when the substitution in the numerator gives you 0. Maybe we can say that a different way. On the last one, let's do an analogous thing. So let's see, on the last one, that c would have been 3, f of x would have been x squared minus 9, and g of x would have been x minus 3. So when, in this case, something squared minus 9 is equal to 0, and our something is a 3. And in this case, our something minus 3 has to be equal to 0, and that's a 3. So that's all we're saying here. We're just doing a generalized form. Okay? So L'Hopital's rule, can we say that in a slightly different way? Applies when you get the indeterminate form 0 over 0. So I'm going to rearrange. Well, I already did. I retyped all this stuff. So this is what we start with. And I just subtract 0 numerator and denominator. Of course, you can subtract 0 without changing a value, so that's allowed. And then since we had already said, hey, f of c is 0 and g of c is 0, or that substitution, putting 3 into x squared minus 9 or whatever equals 0, well, 0 is equal to f of c. So we're allowed to make that substitution. That's still a truthful statement. Same with the 0 in the denominator, that's equal to g of c. We could have put other things there, but you'll see where this goes in a moment. Well, we're allowed to divide anything we want by 1 and not change the value. That's the only difference. We divided the numerator, f of x minus f of c, by 1, and g of x minus g of c by 1. You didn't really need to do that, but it makes the next step a little more obvious. So now we multiply by 1 over x minus c divided by another 1 over x minus c. Now, this thing I circled, am I allowed to multiply by that? I sure am, because that whole thing is 1 if I was simplifying, but we don't want to do that. We want to rearrange to get a different form. So now what do we have? Maybe I should write this even a little bit differently. We have in the numerator the limit as x approaches c of f of c minus f of x over x minus c. And what is that? That should look familiar. That's y minus y over x minus x. That's slope between 2 points, and x is approaching c, which means, we're not going to have slope at 2 points. We're going to have slope as those 2 points are getting closer and closer together. Slope of a tangent line. In the denominator, we'll just break this into two limits. So the limit is x approaches c of c minus g of x. 2 more y's subtracted over. I wrote those backwards, didn't I? Let's keep them in the same order. X, c, x, c. Y minus y over x minus x, and x is approaching c, so we're not talking about slope of a secant line. Really, that's slope of a tangent line. And so what do we get? This limit is actually f prime of c over g prime of c. It's kind of weird. We started off with f in the numerator, and we were doing a limit, and now f changed to f prime. And the g in the denominator changed to g prime. And so here's L'Hopital's rule. When is this true? The limit as x approaches c of f over g is the derivative of f evaluated at c divided by the derivative of g evaluated at c. That's true if f of c equals 0 and g of c is also equal to 0. Okay. Now, 0 and infinity, I think, couldn't be farther apart in terms of ideas, but if you have the form 0 over 0 or infinity over infinity, you can use L'Hopital's rule for both of those because, well, simple algebra, f in the numerator can be 1 over f in a denominator, and g in the denominator can be 1 over g in the numerator. And so if we think about this, you could rewrite this as the limit as x approaches c of 1 over g over 1 over f, which would give you 0 over 0 if we're thinking about substitution. So we just leave everything as it is and use L'Hopital's rule with f in the numerator, g in the denominator. Okay. So if we're going to be doing limits without doing any limit work, we're actually leaning on continuity. Let's make sure you know that. F is continuous at some x value c, if and only if. You know what that is? I'll give you a second to think. The limit as x approaches c of f is equal to f of c. And so this phrase if and only if is actually called a bidirectional. Usually if statements only go in one direction. And what that basically means is, let's not draw an arrow there. If and only if means if f is continuous, then you know this statement must be true, or if you know that statement is true, then you know f is continuous. We'll need to use that, especially on the free response part of the AP test. Let's come back to that. So earlier, we did this limit using some algebra techniques, and we got 6. But let's see if we can use L'Hopital's rule. So in our head, or maybe let's do it on the paper first. So we'd substitute 3 squared minus 9 over 3 minus 3 is 0 over 0. Okay. We actually missed something there, and what we missed is that continuity. Really, we should be talking about continuity first. So let's go back and fix that. So x squared minus 9 is continuous. We know that. We're not talking about the whole quotient, just the numerator. And because of that, the limit as x approaches 3 of x squared minus 9 we can do through substitution, and we get 0. X minus 3 is also continuous. And remember, what does that mean? If you know a function is continuous, that means instead of doing the limit, you can just do the substitution. Okay? And what do we get when we evaluate the limit? Need parentheses. As x approaches 3 of x minus 3, we get 0 is there. We get 0 there as well. So now we have to write using L'Hopital's rule. I'll come back to why that's so important to write in a moment. So using L'Hopital's rule, we actually keep this limit as x approaches 3 out front the same. let's go back. What was that? L'Hopital's rule is, hey, we have f in the numerator, and then we use f prime in the numerator and put that c inside. Okay, so it's a little bit weird. So x squared minus 9, we take the derivative of x squared minus 9, 2x, and write that in the numerator. The derivative of this x minus 3 in the denominator is simply 1. And so now we just get, oh, 2x over 1, that's continuous. So we just get 6. We can make that substitution quite easily. Or that's the same 6. Now I said we have to write using L'Hopital's rule, and yes, we want to do well on the AP test, but maybe there's a better reason. No, there's probably not, but let's think of some logic. If this is all the work that I had, I didn't have any of this and didn't have a giant space in between. Well, this limit as x approaches 3 is in the same spot, so that hasn't changed. And then where x squared minus 9 over x minus 3 used to be is now this 2x over 1. And so because nothing else is written, what does this imply to the reader? It implies, hey, x squared minus 9 over x minus 3 is the exact same as 2x minus 1. That's what your work says. Which is why we need all of that stuff that I had previously written. Okay, you ready for another limit? Okay, limit as x approaches 3 of sine x over x. What are we going to do first? We're going to substitute. Oh no, we're going to zoom in. So stop it. I don't know what's going on. Why do I have a hand? Well, there we go. Now it's back. So you get sine of 3 over 3, and we're done. And why are we done? You were thinking use L'Hopital's rule. No, we are thinking when does L'Hopital's rule apply? Well, where is sine of x over x continuous? Almost everywhere. Everywhere except for 0. And since sine of x over x is continuous at 3, all we have to do is substitute and we're done. Be careful. Don't just use L'Hopital's rule without thinking. Okay, so let's think a little harder this time. At least sine of x over x is undefined at x equals 0. What do you get when you put 0 into sine of x? 0. What do you get when you put 0 into x? 0. So, okay, we have this form, 0 over 0. L'Hopital's rule applies, but we still have to write a bunch of things. So the first thing we're going to do is say sine of x is continuous. Because now we can do an easy limit. So the limit as x approaches 0 of sine of x is the same as sine of 0, which is 0. Okay. And x is continuous as well. So the limit as x approaches 0 of x is also 0. Now what do we write? We say, hey, we're going to do a derivative of this thing, which doesn't seem likely, but we're allowed to using L'Hopital's rule. And so the limit as x approaches 0 stays out front. And instead of sine in the numerator, we write the derivative of sine in the numerator. That's cosine. Instead of x in the denominator, we write the derivative of x, which is 1. Cosine is continuous, so we can just substitute. Cosine of 0 is 1. Divided by 1 is 1. All right, new limit. The limit as x approaches 2 of cosine of x over x minus 2. So, this thing is not continuous at 2, so does L'Hopital's rule apply? It does not. If you substitute in the numerator, we get cosine of 2, which, I don't know what cosine of 2 is. And 2 is more than pi halves, so cosine of 2 is some negative number between -1 and 0. Divided by, well, don't forget, that 0 really isn't a 0. It's really small numbers. What happens when you divide by very, very small numbers? Here's what I would write. Here's my answer. The limit does not exist. Why not? Due to unbounded growth. Maybe as I design this lesson, I'm thinking of something, and that is, yeah, you need to use L'Hopital's rule, but at this point in the year, no, you just have to figure out what to do, and that's the hardest part of the AP test. It'd be really easy if it would say, hey, use L'Hopital's rule, but no, you have to figure that out. So when you're given a limit, you have to think all the limit things you know and what do you do, which is why I'm giving you these mixed up examples. You ready to move on? All right, the limit as x goes to infinity of sine of x over x. Well, what's sine of infinity? It's not really a number, is it? So let's think about what sine looks like. As we move way down this curve, what happens to sine, this function in the numerator? It just bounces in between 1 and -1 to 1 and -1 and every number in between. When does that stop? Never. As we go farther to right, a million, a billion, a trillion, is sine getting closer to 1 or to -1 or to 0? It's not doing any of those. It just keeps bouncing back and forth. So maybe we write it this way. So sine at infinity is some number, almost random, between -1 and 1. Inclusive. And what about x? As x goes to infinity, that grows forever. We say grows without bound. Well, I don't know if L'Hopital's rule applies or not. Actually, it doesn't. We definitely don't have 0 over 0. And, uh-oh, that's not what I want. We also definitely don't have infinity over infinity. The infinity in the denominator, yeah, sure, that works. But the numerator, well, some number between -1 and 1 is definitely not the infinity in the numerator here. Okay. But we still have to evaluate this limit. So maybe we think numerically. So -1, we can use the squeeze theorem, is always less than or equal to sine of x is always less than or equal to 1. Divided by x, divided by x, divided by x, limit, limit, limit. Okay, so as x goes to infinity for -1 over x, we're thinking let's substitute in a million, let's substitute in a billion, and let's substitute in a trillion. Well, what's 1 divided by a million? 1 millionth. Ooh, -1 divided by a million. -1 tenths, hundredths, thousandths, 10 thousandths, 100 thousandths, 1 millionth. Okay. That's when x equals 10 to the 6th, a million. When x equals 10 to the 9th, normally I'd be doing this in my head, but it's hard for you to see what's in my head. We get negative 1 billionth, and when x equals a trillion, we get -1 trillionth. I think it's fairly obvious, maybe you do at this point, the limit as x goes to infinity of -1 over x is 0. Now, some of you know what's going to go on over here for the limit as x approaches infinity of 1 over x. Let's think through that. Let's use a million, a billion, and then a trillion, see if we can find a pattern. 1 divided by a million, 0.000001. 1 divided by a billion, 0.00000001. I counted that on my fingers. That was enough zeros. And then 1 divided by a trillion, 0.0000000001. Okay, I think that for sure is approaching 0 as well. So we can say the limit as x goes to infinity of sine of x over x is definitely 0. Not L'Hopital's rule, but definitely limit stuff you need to know. Maybe this next one's L'Hopital's rule. Let's find out. Limit as x approaches infinity of 2x over x squared. Well, if you substitute 2 times infinity, and this is what makes infinity not a number, is infinity. And infinity squared is weirdly also infinity. Different size infinities, but sort of the same as well. So L'Hopital's rule applies, and we're going to say what? The limit as x approaches infinity of 2x is infinity. The limit as x approaches infinity of x squared is infinity. So we can say, using L'Hopital's rule. So we're going to have the limit as x goes to infinity still. Numerator, the derivative of 2x is 2. Denominator, the derivative of x squared is 2x. And the limit as x approaches infinity of 1 over x is definitely 0. Well, I don't think I do it that way. Maybe L'Hopital's rule, really, we should have those limits equal to 0. So let's rearrange. The limit as x approaches infinity. Let's take the x squared in the denominator and become 1 over x squared in the numerator. And in the numerator, 2x becomes 1 over 2x in the denominator. And so now you get 1 over infinity over, oh no, another 1 over infinity, which is 0 over 0, and you can do L'Hopital's rule that way. Although I gotta tell you, I think all of that is a terrible idea. I don't think I'd do any of that. I'd probably just do this the easy way, even if it's on the AP test. If you did all that, I think you're kind of showing you don't know what to do. Because here, what I would think is, well, maybe we do this numerically. If I was going to do this limit numerically, I'd use a million, a billion, a trillion, always a good starting spot. 2 times a million over a million times a million is 2 over a million. I don't like that there. Let's put it below. 0.000002. 2 times a billion over a billion times a billion I think I missed a 0. And 2 times a trillion over a trillion times a trillion. Okay. And you probably wouldn't write that. You'd do that all in your head, or maybe you'd think, hey, I'm using an end behavior model. Really, only thing that matters since we're using such large numbers is 2 divided by x, because one pair of x's will always divide, and we will say, hey, this limit is equal to 0. Now, I think I'm going to think about e to the x graphically. E to the x looks like this, and x squared, maybe I should draw it underneath. Let's draw x squared underneath. X squared looks like this. And so the limit as x goes to infinity of e to the x is infinity. The limit as x goes to infinity of x squared is also infinity. Hey, this is the time for L'Hopital's rule. So maybe we should say that. Limit as x goes to infinity of e to the x is infinity. The limit as x goes to infinity of x squared is also infinity. So using L'Hopital's rule, we keep that limit out front. X approaches infinity. The derivative of e to the x, that's our favorite derivative, e to the x, natural log. The derivative of x squared is 2x. Well, what do you do now? You try substituting again, except for the limit as x goes to infinity of e to the x is still infinity. And the limit as x goes to infinity of 2x is infinity as well. What you'll find when you take calculus BC is you can use L'Hopital's rule multiple times. But this video is made for my AB students, so we're not going to do that. Just a preview of what's to come. All right, we use L'Hopital's rule here. Maybe there's something better. Let's think about this. 0 plus sine of 2x is 0 over 0 minus 0. Oh, okay, cool. This is 0 over 0. L'Hopital's rule applies. So what are we going to say? Well, we're going to say, oh, we forgot about continuity. X plus sine of 2x. It's continuous. We don't have to do a whole lot of work. And the limit as x approaches 0, x plus sine of 2x is equal to 0. Okay, we don't have to do any hard limit work. X minus sine of 2x is continuous as well. And very similar statement. That limit 0. So what do we say? Using L'Hopital's rule, keep our limit as x approaches 0 out front. And 1 plus cosine of that same 2x, chain rule times 2. No. 1 minus cosine of that same 2x, chain rule times 2. And what do we get? Well, cosine is continuous at 0, so this is going to be 1 plus 2 over 1 minus 2, which is -1, which gives us -3. My screen won't let me write at the bottom. Okay. That should be everything you need to know. If you think I'm crazy writing all this extra stuff, go ahead and check out 2018 number 5 on the calculus AB test, probably different on the BC test, to see, yeah, this really is everything you need to write. And that's, let's see, whatever the last part is. I think it's part C or part D, whatever it is. At the bottom, you have to do the limit. Go check that out. Let me know how it goes.